9:30 we're supposed to start. All right, it's already the last day of Splash 2019. It was an exciting conference. We will have another exciting day. So it's my privilege as a Uppsala program chair to introduce the keynote. But before I do that, I would like to point out that a conference like Splash is organized mostly by volunteers, starting with all the student volunteers, but also all the way up to the general chair. And as Splash and SIGPlan in general, we're looking for volunteers to help us organize future conferences. So if you're interested in organizing or being part of the organization of Splash, let us know. Get in touch. All right, with that, it is my honor and privilege to introduce today's keynote. Our keynote speaker is Işıl Dilek. I think I got it right.
Yes, you got it right.
Excellent. Işıl is an associate professor at UT Austin in Texas. She has done work in program analysis, verification, and especially program synthesis. And she has an impressive list of publications and awards. And she graciously suggested we start at 9:30 instead of at 9, sort of preempting my half-hour introduction of the keynote. So with that, I will not take further time and give the floor to Işıl.
Thank you very much for the introduction, Elko. Good morning, everyone. So as Elko said, I'm Işıl Dilek from UT Austin, and I'm going to tell you about some of the work we've been doing over the last 2 years or so on providing programming support for evolving database applications. Now, before I start, I want to say two things. So first of all, a lot of the credit for what I'm going to talk about today actually goes to my fantastic PhD student, Yopang Wang from UT Austin. And I also wanted to briefly mention that Yopang is graduating this year, and he will be on the job market if any of you are looking to hire. There goes my little advertisement. Okay. And second, I really would like to take this opportunity to thank the conference organizers, in particular Jannes and Elko, both for doing an absolutely fantastic job with the conference organization, and also for inviting me to give this keynote. It's really an honor to be here. All right, so with that, let's get started. So as you can tell from the title, this talk is going to be all about database applications, which basically generally means just a program that interacts with some underlying database. Now, in my opinion, we in the Uppsala community, and more broadly in programming languages, need to be paying much closer attention to database applications because they are everywhere. So just to give a few examples, things like dynamic web applications, enterprise software, customer relation management applications, and so on, all of these interact with an underlying database. And because database applications are so ubiquitous, there's quite a bit of an ecosystem around there. So to give a few examples, you can find various libraries and frameworks like Ruby on Rails, Django, PHP, MySQL, and so on that aim to simplify the development of these database applications. However, it turns out that despite the existence of all this ecosystem, one common pain point during the evolution of database applications is what many people refer to as schema refactoring. And for those of you who may not have heard this term before, that basically means you have to make some sort of modification to the database schema, for instance, either for performance or maintainability reasons. So let me give a few examples of common schema refactorings. So one common example is splitting relations. So you may have one relation or one table in your original schema, but for whatever reason you decide that you need to split it into multiple relations by introducing new primary and foreign keys and so on. So the dual of splitting is, of course, merging tables. So you may have multiple relations in your original schema, and you may decide to consolidate them into a single table. Another common kind of schema refactoring is what's known as denormalization. And essentially, this means that you want to add some redundant attributes, typically with the goal of improving the read performance of the application. And an even more extreme example of a schema modification is when you want to change the type of the database altogether. So for example, your original application may be using a relational database, but for whatever reason, you decide that a graph database, for instance, suits your needs better. Now, while these schema refactorings are quite common, it turns out that from a developer's perspective, these kinds of structural schema changes have significant implications from the developer's perspective. They turn out to be a real pain. And to see why, basically, whenever a developer changes the schema, there are two things that need to happen. So the first is data migration, right? So basically, this means that you need to move or transform the data from your source schema to the target schema. But that's not the only thing that you need to do. In addition, you also need to migrate the code. And by that, I mean you need to re-implement parts of the program that are affected by your schema change. Now, among these two aspects of schema refactoring, the first problem, namely data migration, has attracted quite a bit of attention in the research community, both in programming languages as well as in databases. For example, there's been a lot of recent work on providing data migration support using approaches like programming by example, for instance. On the other hand, this code migration aspect of schema refactoring has received relatively little attention, and if you look at how things are done currently, it's mostly manual. A developer needs to sit down and they need to re-implement parts of the application that are affected by the schema change. And of course, that is not optimal. So this is where our recent research comes into play, because in the past 2 years or so, we have been developing program verification and program synthesis techniques with the explicit goal of helping programmers with this whole schema refactoring process. And in the remainder of the talk, I'll tell you about what we've done so far, but I want to point out that I consider what we've done so far as just a starting point for a longer-term research agenda, and it is not by any means a finished body of work from my perspective. And in fact, my goal or my secret agenda in this talk is to convince some of you in the audience that there are lots of open and interesting research challenges, and I'm hoping that this talk will inspire some of you to join us in tackling some of these remaining problems. So with that, I'd like to introduce a simplified setting that we're going to be focusing on in the rest of the talk, which is what I call parameterized SQL programs. And in particular, it turns out that the problem that we're dealing with is already quite hard. So database applications in the real world tend to be very messy and gnarly. So in the work that we've done so far, we've been focusing on this simpler setting of parameterized SQL programs. So let me explain what I mean by that. So basically, a parameterized SQL program consists of a set of methods, or sometimes I'll refer to those as transactions. And each method takes some input, but its body is going to be straight-line SQL code. So notice that this has two implications. First, we're only going to be considering relational databases. And second, because we're restricting the body to SQL code, that means we're not considering this interaction between SQL code and code that's written in general purpose languages like Java, Python, and so on. Now, furthermore, within this setting of parameterized SQL programs, I'm going to classify each method as either being an update transaction or a query transaction. So in particular, a query transaction, like getName over here, can basically make some database query and returns the result to the user, but we're going to assume that query transactions do not modify the database. On the other hand, the update transactions, like insert user over here, can make arbitrary modifications to the database. They can do insertions, deletions, they can update existing tuples. But just for simplicity, we're going to assume that the update transaction doesn't return a tuple read from the database back to the user. And this is not a fundamental restriction, but I'm just making this assumption to simplify things. Okay. So with that, here is a brief outline for the rest of the talk. So in the first part of the talk, I'll tell you about some of the work we've done on proving equivalence between a pair of parameterized SQL programs. And this is going to be based on our POPL 18 paper. And this verification problem is important for code migration because we want to certify that, that we haven't modified the functionality of the application before and after schema change. Now, after we talk about how you can verify equivalence, then I'm going to tell you how you can leverage this verification algorithm to solve the more ambitious synthesis problem. So this part of the talk will be based on our recent PLDI 19 paper, and the problem we're addressing here is, given the original database application and the new schema, how do we automatically generate the new version of the application? And then finally, in the last part of the talk, I'll talk about some of the problems that we've encountered that we are aware of, but we haven't yet solved, and I'll talk about some future research directions in this space. All right, so let's start with our verification problem. So to remind everyone, the problem we're solving in this context is the following. So we're given two database programs, and again, we're restricting our attention to parameterized SQL programs. And these programs interact with different schemas, and we want to know, are these two programs equivalent before and after schema change, or did we mess something up and introduce a bug and break the existing functionality? Now, before I talk about how we're going to do verification, let me first introduce a little running example that I'm going to refer to, at least in the first half of the talk. So basically on this slide, you can see a little fragment of actually a real-world application called Connected Diagnostics Platform. And this application allows users to subscribe to a service and then get notified about the results of various medical tests. And as you can see here, we have methods called createSub for creating subscribers. It allows you to update subscribers, and it also allows you to query information about subscribers. And if you stare at this code for a second, you will see that among other relations, it interacts with a table called subscriber. And as you may expect, this subscriber relation stores some identifiers and the names of the subscribers. And it also has this filter, which basically stores the condition under which the subscriber will be notified about the results of their medical tests. Now, it turns out that during the evolution of this application, and I'm not making this up, this is something that we actually found in the GitHub commit history, the developers decide that having just the subscriber relation is suboptimal, so they decide to split the subscriber table into two tables. So in particular, they introduced this new table called filter, and the old subscriber table, instead of directly storing the filter, it now has a foreign key that basically points to the relevant tuple in the filter table. So now, of course, after you refactor the schema in this manner, you also need to go ahead and re-implement the code over here. And in this case, this is the new version of the code. And to point out a few things, so in the previous version of the createSub method, it was just used to be a simple insertion, but now, of course, you have to insert into two different tables. And if you look at the updateSub method, it just used to be a simple update, but now you need to do a nested query over here. And finally, for the getSubFilter query transaction, it used to be just a select from a single table, but now you at least have to take the join of these two tables. So the question we want to answer is, given the original program and this new one, are these implementations actually equivalent, or did we introduce a bug somewhere? So in order to answer this question, first I want to be precise about what we mean by these two applications being equivalent, because this is not obvious in that context. After all, they interact with databases that have different schemas, so we can't just say that the state of the database needs to be the same. So what do we even mean by equivalence? So to answer that question, let's say we have two programs P and P prime, and we're assuming that they provide the same interface. They provide the same set of methods, but they have different implementations. So in this context, we define equivalence in terms of observational equivalence, which basically means that the same actions result in the same outcome or observation. And if you apply it to our setting, the actions correspond to updates on the database, and the observations correspond to making queries, right? So to be more concrete, basically we're going to say that P and P prime are equivalent if every query transaction exposed by our program yields the same result after invoking the same sequence of update transactions on the program. And of course, we're assuming that the arguments that you provide are also the same. So now, going back to our running example, here we have two update transactions, create sub and update sub, and a single query transaction, get sub filter. So therefore, for these two programs to be equivalent, basically we require that get sub filter for the same identifier must yield the same answer after an arbitrary sequence of colon create sub and update sub transactions. So that's what it means for these two programs to be equivalent. Okay, so now we discussed what equivalence means. So now let's talk about how we're actually going to prove equivalence. So the basic methodology that we use to prove equivalence is fairly simple and quite standard, and it relies on finding a so-called bisimulation invariant. And in particular, in this case, the bisimulation invariant is going to relate the database states of the two programs. So for instance, the bisimulation invariant may say something like this: A equals B join C, where A may be a table in the original schema, and B and C may be the new tables in the refactored schema. Now, of course, beyond relating the database states, this formula must be an invariant, meaning it needs to hold initially, and it must continue to hold after we invoke a corresponding pair of update transactions. Okay. Now, of course, just inferring a bisimulation invariant isn't good enough. We also need to make sure that it's strong enough to verify equivalence. But the basic idea is that first we're going to try to infer the strongest bisimulation invariant that we can, and then we're going to see if using this bisimulation invariant we can prove that the query results are pairwise the same. So basically what this means is, let's say we have a corresponding pair of queries Qi and Qi prime, and let's say Qi takes arguments x, and Qi prime takes arguments y after alpha renaming. So we're going to ask, assuming phi holds and assuming we provide the same arguments, can we show that the query results are the same for every pair of corresponding queries? And if the answer is yes, then we have a proof that these two programs are equivalent. So that's the basic idea, but the key question is, how do we actually automatically infer these bisimulation invariants? So in our prior work, we gave a method for automatically inferring these bisimulation invariants. And this technique that we proposed, you can think of it as basically an adaptation of the very well-known Houdini algorithm that's been popularized by ESC Java. And basically what that means in the setting, so first we're going to start with basically a predefined set of predicate templates that's going to relate the two views on the source and the target database. So for example, the templates may say things like projecting some attributes from some table is equal to projecting some other attributes from some other table, or they can be more complicated. They can involve joins, selections, and so on. Okay? So now, given this set of predicate templates, we're going to instantiate these question marks with elements from the source and target schemas, and we're going to generate a universe of candidate atomic predicates. And then given this universe, we're going to perform a fixed point computation with the goal of inferring the strongest conjunction of these atomic predicates that is actually an invariant. So let me elaborate on how that works in more detail. So we start with our predicate universe that we just generated, and then we're going to initialize our candidate invariant to be the conjunction of all of these. So in other words, we start with the strongest possible invariant, right? And then we ask, assuming this is a bisimulation invariant, we haven't yet shown that it is, but for the moment, for the time being, let's assume that it is, then we're going to use an SMT solver to check if this current candidate implies that the query results are pairwise the same. And if the answer is no, we have to give up, right? Because we already started with the strongest possible invariant, so if that's not good enough to prove equivalence, then there's nothing else we can do. On the other hand, if the SMT solver comes back and says, yes, it is strong enough, we still need to ensure that this guy is a bisimulation invariant. So in order to make sure that it is, we're going to check that it is inductive. So in other words, we're going to show that it holds for the initial pair of databases. And then we're going to ask, assuming phi holds, and assuming we execute a corresponding pair of updates, can we prove that phi continues to hold? Okay? And in order to do that, we're going to generate verification conditions and hand those over to our favorite SMT solver. And if the SMT solver says, yes, the VCs are valid, then great. We found something that's both a bisimulation invariant and strong enough to prove equivalence. So we're done. But if it's not, we don't have to give up just yet, right? So in that case, we're gonna see if there's something weaker that's still good enough to prove equivalence. So in particular, we're going to identify which of our atomic predicates is not preserved by the updates. We're going to remove that to get a weaker invariant. So basically, the new bisimulation invariant just now excludes one of these. And then we keep going until we either get to a state where the current candidate is either too weak, or hopefully we can find something that's both an invariant and strong enough to show equivalence. So that's the high-level picture. And to recap, what we've done so far is I discussed the technique that takes two parameterized SQL programs, and it gives a yes-no answer saying whether it is verified or not. And of course, this is not just an idea in theory. We also implemented it in a tool called Mediator. And I do want to point out, however, that there's one limitation of this technique, which is that it can be used for verification, but not for falsification. So in other words, if Mediator says, yes, they're equivalent, our technique is sound, so we know that the programs are equivalent. But if it says it's not verified, we could possibly have a false positive. So it could be that the programs are not equivalent, but it could also be that whatever bisimulation invariant we inferred isn't good enough. So, but despite this limitation, at least we now have a way of, of soundly proving that two applications are equivalent. All right, so that concludes the first part of the talk. Now I want to show you how we can leverage this verification algorithm to address our synthesis problem. Okay, so to remind everyone, the synthesis problem we're solving, the problem is the following. So again, we're given the original program, and still I'm assuming that it's a parameterized SQL program. And we also have the new schema, let's say S prime, and the goal of the synthesizer is to generate a new program that's going to be over the new schema, and it must be provably equivalent to our original program. We don't want to just, give something that doesn't have any guarantees. We want to show that it's equivalent. And from a very, very high level, our synthesis algorithm will leverage an enumerate and verify approach. So in other words, we're going to enumerate a sequence of programs that may possibly be equivalent to the original program. And then we're going to use this mediator tool that I talked about, our verification algorithm, to check if they're actually equivalent. So that's the basic idea. Okay, but of course, as in any program synthesis technique, the key challenge that we need to address is that the search space is very, very, very large. So if you try to do this enumeration in a naive or very brute force way, this is not going to scale. So in order to address this challenge, our synthesis algorithm is going to decompose the problem into two parts. So first, we're going to generate a so-called program sketch. So rather than enumerating complete SQL programs, we're instead going to enumerate possible sketches. These are going to just give outlines of the program. And then for each sketch that we generate, we're going to hand it over to a different algorithm, and we're going to ask, is there completion of the sketch that's equivalent? So let's see how this works more concretely. So first of all, in order to generate a useful sketch, what our technique does is it takes the source and the target schemas, and it infers or conjectures a so-called value or attribute correspondence. And basically, what I mean by value correspondence is it's a mapping from the attributes in the source schema to attributes in the target schema. And this notion is quite general because the mapping doesn't need to be one-to-one. It can be one-to-many, many-to-one, or even many-to-many. And if you ask me, why are you inferring this value correspondence, how does that help? There are two reasons why we do this. The first reason is it turns out that if you can infer this value correspondence, it will make it a lot easier to generate a useful sketch that restricts our search space. But the second reason is it turns out that just by looking at the names of the schema elements, names of attributes, tables, and so on, you can guess the intended value correspondence relatively easily. Okay? So then once we have this value correspondence, we're going to use it to mechanically generate our program sketch. And in this context, a sketch is going to be a SQL program where the names of the attributes and the tables are unknown. And the value correspondence will tell us how these holes can be instantiated. So it's going to constrain the domain of each unknown in the sketch. So then once we have our sketch, we're going to hand it over to our solver, and I'll get to that in a second. And the solver is going to be tasked with finding a completion of the sketch that is equivalent to the original program. And if it succeeds, great, we're done. But otherwise, that means our inferred or conjectured value correspondence was wrong, so we basically move on and try something else. That's the basic idea. Now to see how this works more concretely, I'm going to, again, introduce a little example. And the example that I'm showing on this slide is fairly simple to fairly similar to the verification example that we looked at, but it happens to be just a bit more interesting from a synthesis perspective. So it's not really important what the code here does, but the basic idea is you have some program that allows you to query information about courses, including instructors and TAs. And unsurprisingly, we have two relations that store information about instructors and teaching assistants. Okay, so now let's say in our refactoring, similar to the previous scenario, we want to introduce a new picture table, and rather than directly storing the pictures in the original tables, we have a pointer to the new picture table. So the question is, given this original program and this new schema, how can we automatically derive our new program that's in a way that's equivalent? So as I just mentioned, the way we're going to do it is to start with, we're first going to guess a value correspondence. That's going to say this attribute in the source schema maps to this attribute in the target schema. And if you just stare at the names of these attributes, this isn't too hard to guess. You can say, oh, probably the I pick in the instructor table will map to the pick column on the picture table, similarly for this one. And it's also not too hard to guess that ta.tname will still map to the same thing, ta.tname, and similarly for ta.id. Okay? So now let's take this value correspondence and see how we can generate our program sketch. And since since our technique is going to generate the sketch one method at a time, I'm just going to focus on this single query transaction, get TA info. And as I mentioned earlier, when you generate the sketch, this is basically going to give you the outline of the program, but the attributes and the tables will all be unknown. So we have a bunch of holes in the sketch. Okay, so now what we're going to do is let's see what's the domain of each hole under our inferred value correspondence. So for question mark 1, in the original program, it corresponds to tname, and our value correspondence tells us tname still maps to tname, so there's only one possibility for that. Similarly, we can make the same similar reasoning for question mark 3 and question mark 4, so those all have a single possibility. But if you look at this question mark 3 over here, that's a little bit more interesting. So in particular, question mark 3 needs to be filled with an expression. This can either be a table or it can be a join chain. But whatever it's instantiated with, it must be a view that has at least these 3 columns, tname, pick, and TAID. Okay? And if you look at the target schema, you can see that there isn't a single table that has all of these attributes, but you can obtain it by taking the join of existing tables. And in particular, here we have 2 possibilities. So you can either fill it with picture join TA, or you can take the 3-way join of picture TA and instructor. And if you continue in a similar way with the remaining 2 methods, we can obtain the sketch for the whole program, and in this particular case, this corresponds to a search space of 64 concrete SQL programs. Okay, so now we have a way of mechanically deriving our sketch from the value correspondence, but how do we solve it? How do we find a completion that's equivalent? Well, you might say, well, this is really simple, right? The sketch basically corresponds to a finite search space, so let's go ahead, enumerate all the programs, and in our example, we have 64 possibilities. We can just use our verification algorithm to check if they're equivalent. Well, that works in principle, but it's never going to scale in practice, right? To see why, let's take a very simple sketch. Let's say we have a small sketch that just has 15 holes. And let's say each hole has just 3 possibilities it can be filled with. Well, then our search space will contain over 14 million programs. And remember, for each program we enumerate, you need to invoke the verifier to check if they're equivalent. And verification, as we all know, isn't cheap, right? It can, in this context, it can take in the order of tens of seconds or even minutes. So this is not going to work. So in order to make this technique practical, we basically use this idea of conflict-driven learning for synthesis to prune the search space, and this is actually an idea that we introduced in an earlier PLDI 18 paper. So let me briefly explain what I mean by conflict-driven learning. So as it turns out, this idea of learning from conflicts is nothing new. It's actually something that's completely standard in the automated theorem-proving community. Modern SAT and SMT solvers are completely based on this idea of learning from conflicts. But in the context of program synthesis, learning from conflicts means the following. So whenever you enumerate a program that's incorrect, you want to do some inference. You want to think, you want to do some root cause analysis. And you want to infer a set of other programs that are also provably incorrect, that don't meet our specification. And as I mentioned, we introduced this idea of learning from conflicts in a previous paper, but that particular technique isn't applicable to this setting, because there we were dealing with programming by example, and we certainly weren't considering SQL programs. So in order to leverage this idea of learning from conflicts in our context, we basically introduce a new concept called minimum distinguishing input. So let's see what that means and how that helps us do conflict-driven learning. So first of all, before I continue, let's recall that an input to a database application is a set of function invocations along with their arguments. So unlike, what you might think of, you typically think of an input as just being an integer or a string or something like that. But in this case, it's going to be an input is a set of or a sequence of function invocations with their arguments. Okay, so for instance, if this is our database program, an input may look like something like this. So it says first add a specific TA, then you query the information for that TA. Now, we're going to say that an input is distinguishing for a pair of programs P and P prime if executing I on P yields a different query result than executing I on P prime. So in other words, a distinguishing input is a counterexample to equivalence. It's a witness to the fact that these two programs are not equivalent to each other. So how does that help us? How will this help us learn from failed synthesis attempts? So the idea is the following. So let's say we're given our original program P, and let's say we enumerated a program P prime. That's incorrect. It's not equivalent. Now, since they're not equivalent, we can go ahead and ask and hopefully find a distinguishing input. Let's say I. Now, here's the key observation. So in general, our program P is going to be large. It can contain hundreds of transactions. So basically, the number of functions in it will be a large number, n. But even in the context where P is large, you can typically find a counterexample to equivalence that's small. So typically you can find a distinguishing input that uses only k functions where k is much, much smaller than n. So k could be something like 2 or 3 where n is in the order of hundreds. So now, based on this observation, here's the key insight. So basically, we can ensure that any other program, let's say P double prime, that agrees with our incorrect program P prime on just the implementation of those k functions is also guaranteed to be incorrect for the same reason. Why? Because our distinguishing input doesn't even refer to those functions. So as long as, it doesn't even refer to those other functions. So as long as it agrees with these k functions, we know we're doomed. So based on this idea, what we can do is rather than just rejecting a single program, we can reject a whole set of programs. And of course, in general, the smaller the distinguishing input, the bigger the set of programs you can reject. So in general, you want to find a small distinguishing input, meaning it should invoke as few transactions as possible. So let's see how that helps us in our running example. So let's say we enumerated this program, and this happens to be incorrect. It's not equivalent. If you invoke our verifier, it will tell you, no, they're not equivalent. And in this case, we can go ahead and ask for distinguishing input, and the input I showed you earlier happens to be distinguishing. In particular, if you execute this on the original program, it will give you the desired TA, but if you execute it on this program, it will just give you nothing. So now, based on this distinguishing input, we can conclude that the assignments to the holes in delete TA are irrelevant because our distinguishing input doesn't even refer to this function. As long as as long as you keep the same implementation of add TA and get TA info, no matter how you implement this delete TA method, you're going to get something incorrect. And in this particular case, because the sketch for delete TA can be instantiated or filled with 14 different ways, that means we can use this information to rule out 14 programs in one go rather than just rejecting a single program. So that's the basic idea. But going back to the big picture, the main ideas that one should take away from this discussion is if you want to make this synthesis technique work, there are two key ideas. One of them is rather than enumerating SQL programs, you first want to generate a sketch, and we do this using this notion of value correspondence. And if you want to be able to solve the sketch in a practical way, then we use this notion of distinguishing inputs to enable learning from failed synthesis attempts. Those are the two key ideas. Okay, so that's all the technical detail I wanted to talk about. Now, let's talk about whether this works at all in practice. So to evaluate this technique, we implemented a tool. This tool is called Migrator. And if any of you are interested in playing with it, just trying it out, building on top of it, it's open source, and you can get it from our group webpage, which is github.com/utopia-group/ the name of the tool, Migrator. So to evaluate this approach, what we did is we collected 20 benchmarks that correspond to tricky schema refactoring scenarios. And where do they come from? About half of them, actually exactly half of them, are taken from textbooks and online tutorials. In particular, we took a bunch of examples from this textbook called Refactoring Databases by Ambler and Satterledge. And we also wanted to evaluate this on real-world programs, not just textbook examples. So we collected a bunch of Ruby on Rails programs from GitHub, and in order to do that, we wrote a crawler. And we looked for 2 consecutive GitHub commits where the schema was different between the 2 commits. So half the benchmarks come from real-world applications. So in case you're wondering, to give you some context, some statistics about these benchmarks. So for the textbook examples, they're relatively small, as you may expect. So they have around 10 transactions, 2 tables, and 8 to 9 attributes. But unsurprisingly, the real-world programs are much larger. So they have over 100 transactions, over a dozen tables, and over 100 attributes on average. Now, in terms of the key results, the main takeaway is that we were able to successfully generate the new version of the program, and furthermore, all of these programs were proven to be equivalent to the original program. And in case you're wondering how long does this take, well, it's actually reasonably practical. So for the textbook benchmarks, the average synthesis time, including verification, is around 6 seconds. And for the GitHub benchmarks, even then it's quite reasonable. So the tool can synthesize programs with over 100 transactions in a matter of minutes. It takes about 2.5 minutes on average. Okay. So I don't want to overplay the importance of these results because, as I said, we're still working in the simplified setting of parameterized SQL programs. But I do think that these results indicate that there is some hope of being able to automate code migration when you refactor databases. And there are 2 key ideas that allowed us to do this. One is you need a way of verifying equivalence, and the other one is you need an algorithm that allows you to efficiently explore the space of programs that are potentially equivalent. All right, so now to conclude, I want to talk a little bit about the future directions, the problems that we haven't yet solved. So as I mentioned at the beginning, I consider what we've done so far to be a good starting point for addressing this problem, but as you can imagine, there's still a lot of work that remains to be done. So I'll just talk about some of the next steps that I'm interested in. So the first, or the most obvious next step here is, generalizing this from this simple setting of parameterized SQL programs to real-world database applications. And there are several challenges in doing this. So one of them is in our simplified setting, we just looked at SQL code. We did not consider the interaction between SQL and general purpose programming languages like Java, Python, whatever. So this is obviously a challenge that we need to address in future work. Another challenge is in this context of parameterized SQL programs, we assume that all the SQL code was statically available, but in reality, it may be more complex. So in the simplest case, you may have some control flow. If this condition holds, then do one SQL statement, otherwise do something else. And in more complicated cases, this may actually be dynamically generated. You may be building it up dynamically. And another challenge that's related to the first point over here is we assume that methods can take user input, but this user input is fed directly as query parameters. But in reality, programs can do computation on either the query result or the input to the query. And again, this is a challenge that we have not yet considered. Now, the second research direction that I'm interested in pursuing is generalizing this idea from relational database applications to NoSQL database applications, which are increasingly growing in popularity. So in particular, what I'm interested in, given, for example, a relational database applications, and if the target is some other type of database, like a graph database, can we automatically migrate the code in that case, for instance? And again, there are several challenges here, both on the verification and synthesis side. So one on the verification side, well, obviously the problem is much harder because you have very different data models, and on top of that, you're going to get programs that are written in different languages. For instance, SQL versus Cypher for graph databases. And I also would anticipate that the synthesis problem will be more difficult because I would imagine that the value correspondence in that setting is going to be more complex, so that will mean your search space is larger. So that's another challenge. And finally, another direction that I'm interested in is coming up with a unified framework that allows us to do verification and falsification in a synergistic way. And as I mentioned at the end of the first part, the technique that we proposed in our earlier work can prove equivalence, but it cannot be used for falsification. It doesn't give you counterexamples. So to address that shortcoming, I'm interested in looking at approaches, for example, based on counterexample guided abstraction refinement that can look for proofs and counterexamples, hopefully in a synergistic way. So basically, the main point I want to make is, I do feel that this is an exciting research area at the intersection of programming languages and databases, and there is a lot more work that remains to be done, and I really hope that some of you in the audience will start working on these remaining problems. So to conclude, I just want to acknowledge my collaborators. So as I mentioned at the beginning, the lion's share of this work was done by my PhD student, Yopang Wang, so he deserves most of the credit. And I also want to say that I've had the pleasure of working with two absolutely fantastic UT Austin undergraduates. So one of them is Rushi Shah, who's a senior, and I'll also advertise that he's looking for grad schools. And the other one is James Dong, who's a junior at UT Austin, and both of these guys had significant contributions to the synthesis aspect of the project. And finally, I also want to acknowledge my collaborators, Shuvendra Lahiri from Microsoft Research, as well as William Cook, my colleague at UT Austin, who's actually here. And both of them also had valuable contributions to this project. So with that, I'll conclude, but I'm happy to take any questions.
All right, thank you, Ishil. Indeed, we have time for questions. Anyone? John over there?
When you're conducting your search, then very many of the programs that you consider will be obviously wrong.
Right.
Have you considered just running a few random tests to eliminate programs before you start trying to verify?
That's what we do, actually. That's exactly what we do. And, I mentioned that our verification algorithm isn't capable of giving counterexamples, and that's how we get these distinguishing inputs. We just run tests. So in practice, you only do the verification in the last step.
So if you have questions, please line up in the, and then that may be more efficient to, but go ahead, Anders.
Thank you for a great talk. So on these 20 programs that you considered, I guess you spotted some patterns in how people do these schema evolutions. So I wonder if you could maybe exploit some of these patterns and see these are like 5 different common ways people typically make these changes, and then take advantage of that?
Yeah,
instead of having this super general technique?
I guess some of that, for instance, the common kinds of, for example, as I mentioned, this verification algorithm is using a Houdini-like approach. So you have these predicate templates. So I guess you can think of those templates capturing the common patterns in some sense, yeah.
Thanks for the talk. This was very interesting. You were talking about databases, but actually it seems like there's a very closely related problem that doesn't involve databases at all, which is if you're programming with libraries, the library interface changes and you want to refactor your clients. So I just wondered if you'd thought about that problem or how to transfer your results to that setting.
I do believe that some of these ideas should be applicable, and I think you're absolutely right, but we haven't considered that problem. But that sounds like a really interesting direction for sure.
Other questions? So let me ask a question then. So you've talked about refactoring, right, where you transform the schema to an equivalent schema, but often in database applications we don't refactor, but we add new functionality.
Stuff, right?
So then you cannot talk about equivalence anymore if you thought about those kinds of scenarios.
Yes, exactly. So I didn't talk about it in this talk, but we also consider a notion of refinement, and we have a way of verifying refinement between two applications as well. And when I talk about refinement, I mean that the query result that you get in the original program is a subset of is a projection of the query result on the new program.
Right, and you would discover that projection automatically?
Yes, we do.
Okay.
Yeah. Mm-hmm. Yeah.
Any other questions? Plenty of time.
Good thing I suggested starting at 9:30.
Yeah, you got some extra sleep. Well, then we get extra coffee, I suppose. So let's thank Michel again for a great talk.